Okay, let's go start the class. I think all of you have received my email about the rest of the class, right? We are going to do chapter 8, which is viscous flow in pipes, today and on Thursday. We'll finish chapter 8 in 2 lectures, and then next Tuesday we will have an exam review session, which will focus on chapters 4, 5, and 7. So Reynolds transport theorem, the integral analysis, all of the governing equations, all of those things, and the Buckingham pi theorem, the dimensional analysis in general, chapter 7. And your exam will be on Thursday, so in 4 lectures, including today. After the exam, we will do a lecture on chapter 6. The main focus of that part of the lecture is going to just to expose you to the partial differential equations, the governing equations. So, I mean, you won't have to do. I don't think we will use any of those material on the final exam in the problems. So I may ask you in the exam, like, give me this is something you will become familiar with. What are the Navier-Stokes equations, right? Just write down the equation. As long as you have it in your equation sheet, you should be able to write it, right? So nothing out of the ordinary. And then we will have an exam review session. If we needed more than one final exam review session, we can definitely schedule another time to meet here probably and solve more example problems and answer more of your questions. Is there any questions? Okay. And let's see. One more point that I think I mentioned this in the previous lecture. We will have attendance quizzes every day, right, during the lecture. And this is how it's going to go. Just, I guess, to help you with your grade and just to make sure that you are watching the lectures as well. You don't have to be in class. As long as you watch the lecture online, you're fine. You can just submit your attendance quiz after you watch the online lecture. Well, it has to be in a close time frame, right, to the lecture, like in a week, right? Not the night before the final exam. That doesn't really count as attendance, right? And whoever can give correct answer to, or close to the correct answer to the quiz problems will get a bonus point, right? Okay. So these are not very hard problems. Just have to be able to think a little bit, think out of the box a little bit. Only for bonus points. So viscous flow, and we will have the attendance quiz and in the beginning of the class, which means that we are going to have the attendance quiz right now. Okay. About this topic, we are going to discuss the viscous flow in pipes, right? And this is the question I want you to answer in your attendance quiz. What do you think are the most important parameters? What are the most important parameters when it comes to flow in pipes? Or to rephrase the question, what are we trying to find here? Is it the, I don't know, wall shear stress? Is it the velocity profile? Is it the pressure loss? Is it the energy of the system? Is it the entropy? Whatever. Of course, we are not trying to find entropy because this is not thermodynamics. But so a couple of different parameters, just write them down. And just submit them. Just if you have a question, you can ask the question. There's no cheating or restriction. You can talk to your friends, your colleagues, your classmates. Ask for their opinion. You can ask me. Or as far as your grade is concerned, as long as you're submitting something, you will get the attendance grade. And if you submit the correct answer, you will get the bonus points. Okay, I guess we have had enough time to think about this. If you can just pass your answers to the front. Just give it to your friends. Just pass it up front. You can take the answers from people who are sitting behind you, then pass it forward. And thank you. Thank you. And if you are watching online, just send me an email. Unfortunately, I cannot extend this bonus point thing to the online students because, or I can. It doesn't matter. Yeah, if you submit the correct answer, I will give anyone a bonus point. Okay, so let's answer this question first, and then we'll move on to the topic. What are the things that we are most concerned about when dealing with flow or when analyzing the flow inside the pipes? Flow inside the pipes is one of the more common types of flow that we have to deal with as engineers. That's actually, this is one of the more applied part of this course that you will see if you end up in the oil industry or sewage industry, whatever they call it, or we have different types. In biomedical industry, the blood is moving through pipes, right? Your veins. So analyzing this, understanding this type of flow is actually a very important part of fluid mechanics. There are two parameters that are of utmost importance. That is true for other types of flow, but they are specifically important when it comes to flow inside pipes. Your pressure loss is very important, right? Pressure loss or pressure drop inside the pipe. I'm pretty sure you have heard this terminology before, like pressure drop in a pipe, right? This is something that we need to be able to calculate. And also, in a more micro level, the velocity profile. This, and both of them are directly related to your wall shear stress and viscosity. So, and if you have mentioned any of these in your answer, you will get the bonus point. Okay? So, the goal of this chapter is to somehow relate the pressure loss to the velocity profile and the wall shear stress, and to find the velocity profile in the pipe flow, in flow inside the pipe. There is another term we use for the flow inside the pipe, and that is called internal flow. You will have a whole chapter on internal flows in your heat transfer course. Okay? Okay. So, what are the different types of internal flow? We can have a flow inside the pipe, and the first type is where all of the pipe is covered with your specific fluid. Let's say your fluid is water. If all of the pipe is covered with water, we're going to have the first, this is the first type of the flow. And in this type of the flow, pressure gradient is the main driving factor of the flow. So the change in pressure. This essentially means that your fluid goes from a higher pressure location to a lower pressure location. This is analogous to how electric current moves, actually. Electric current goes from your higher electric potential to lower electric potential, right? That's the idea. Same thing happens here. Your fluid moves from higher pressure location to a lower pressure location. Let's say we have higher pressure here and lower pressure here. What would be the direction of the flow? From high pressure to low pressure. Second type of the flow, which is out of the scope of this chapter, is called an open channel flow. This happens when your fluid does not fill all of the pipe. So essentially, your fluid only covers a portion of the pipe, and the rest of it is filled with with a gas, or in some other cases with another liquid, right? Which means that you are dealing with an interface here, with an open surface or interface. But this type of flow, this is not something we are going to analyze. If you end up taking an intermediate fluid mechanics course, which we don't really offer, sometimes, once in a blue moon, you will see that discussion on the open channel flow. Okay, so we are going to focus mainly on this type of flow, right? But what would be the effect of changing the velocity of the flow, increasing the velocity of the flow? These are the things we need to address before doing the real analysis. We already understand that this type of flow is called the pressure. It's also called, let me mention this as well. It is called a pressure-driven flow. So higher pressure causes the movement on the flow. But what would be, how would the flow pattern change when you change the incoming velocity, when you increase the incoming velocity? Incoming velocity, I'm going to call V infinity, right? Velocity that is happening here. As you increase the velocity, we are going to, your flow pattern is going to go from an orderly or ordered flow to, let's call it a messy flow. This ordered flow, and we're going to see an examples of these two types of flow in a couple of seconds, in a couple of minutes, is called a laminar flow. This messy flow is called a turbulent flow. Okay. So as you increase the velocity inside your pipe, your flow goes from laminar to a transition point to a turbulent flow. Well, what does an ordered flow mean? Pretty simple. Let's say you are inside this pipe, and this is a fluid particle going in at this location. This fluid particle will move like this on a straight line and will go out. The same is true for any other fluid particle, right? And keep in mind that we are not talking about molecules. We are talking about fluid particles. Right? Fluid particles are arbitrary selections of like thousands of molecules. Right? They are bigger than molecules. Right? So a fluid particle comes in, goes out at the same location, comes in, goes out at the same location. Doesn't really matter where it comes in, which essentially means that your velocity profile, if I have to, let's say on this, I'm going to show velocity, and this is y, is going to look like this. If you include the effects of viscosity. If you don't, it will just be a uniform. In this transition, you will see a little bit of fluctuation in the path. So fluid particle comes in, may move, and then go back to the straight line, and something like this. So you will have some parts that have fluctuations. A fluid particle moves, not in the z direction, if you will, or x direction, if you want to call this direction x. But in general, it's a mixture between an ordered movement or a fluctuating movement. But in turbulent flow, as we have increased the velocity, your fluid will move like this. So a fluid particle that is coming at this point may go out of your pipe at another point. That's the idea. So, and there is this guy called Reynolds, Osborne Reynolds, who was the first one to investigate this and classify the type of flow and understand where and when the transition happens, at which velocity transition happens. So let's watch an example of the original experiment. This original experiment was performed in the 19th century And the device, the pipe that the Reynolds, Osborne Reynolds, did the experiment in is actually still available. You can go to UK and see the original experimental setup. So this is the original experiment. See, we have a dye that is coming in through a pipe here. This is your original pipe. It is not very. Let me turn off the lights for a second. Didn't change much then. This is your original pipe, right? You have flow coming in from this direction and going out from here. Then you have a pin type thing that is injecting a dye to your flow, right? As you can see, for a very small velocity, this dye is moving on a straight line, right? So whatever fluid particle is here is going to go out of your pipe at the same location. What will happen if we increase the velocity? Okay, you can see, do you see the fluctuations starting to appear, right? There are some regions that is fluctuating, and there are some regions that are still straight, right, as we increase the velocity. There is a starting point for this fluctuation. We're going to talk about those later. So we are in the transition now. Then these fluctuations become very dominant. As you can see, the dye starts dispersing in the flow, right? And they have increased the amount of dye. But because of the mixing that is happening inside this experiment, let me go back a little. Because of the mixing that is happening here, you can see that dye is dispersing inside the fluid, and at some point you cannot distinguish between the dye and the original fluid, right? Is there any questions? Okay, let's see this one as well, and then
have you ever wondered what's actually happening with water flows? Well, let's take a look. Here we have 3 garden hoses. At a glance, the water flow looks identical, but if we insert a thin, constant dye through each hose, we'll see that the flow is actually quite different. In the top hose, the water molecules are flowing in a very orderly fashion, and we call this laminar flow. In the bottom hose, water molecules are flowing in a very disordered and turbulent manner, called this turbulent flow. In the middle hose, water flow is somewhere between laminar and turbulent flow. We call this transitional flow. Now you may be thinking the hoses are identical, so why is water flowing so differently through each of them? That's a great question. Well, this has to do with how fast the water is flowing. The faster it flows, the more likely it is to be turbulent. There are, of course, other factors that can affect how a liquid flows in the system, including its density, viscosity, and also the diameter of the pipe itself. Reynolds number combines all these variables in such a way that we can predict how a liquid will flow. If you calculate Reynolds number to be less than about 2,000, the liquid will likely to be flowing with laminar flow. Any value above 4,000 indicates turbulent flow, and any value between the two means the liquid is transitioning or fluctuating between the two flows. We'll look at Reynolds number in more detail in future videos, but for now you just need to know that laminar flow is when liquids are flowing in a very ordered fashion, turbulent flow is when the flow is very disordered, transitional flow is a fluctuation between the two flows, and both properties of the liquid and the pipe it's flowing through will determine how a liquid flows. We hope you found this video useful. As always, you can find a link to the written tutorial in the description box below.
okay. So when you're dealing with pipe flow, this type of flow is very important. Are we dealing with a laminar flow, a transition flow, a transitional flow, or a turbulent flow? And as you saw in this video, the velocity is not the only factor determining this type of flow. The pipe, the fluid density, the pipe diameter, the length, all of those things are actually not the length, but the fluid diameter. All of those things are very important. That's actually why we have to introduce dimensionless parameters that is going to help us compare the flow inside different pipes with different diameters with different liquids, right? That was the idea of the dimensional analysis. Dimensional analysis helped us come up with dimensionless parameters that are independent of your pipe diameter, type of the material you're using, right? That was the idea. So Reynolds number. A Reynolds number was first introduced by the same guy who did the original experiment, Osborne Reynolds, in the 19th century. So Reynolds number for flow inside the pipe can be calculated by the fluid density multiplied by its velocity multiplied by the diameter divided by its viscosity. Okay? So it doesn't really matter what type of liquid you have or what type of pipe you have, as long as your Reynolds number is less than 2100, you are within the laminar flow region. And you can use the formulas for pressure drop, velocity profile, those things that we're going to see later, that we find for the laminar flow. And if the Reynolds number is between 2100 and 4000, you are in the transitional type of flow. That this one is the hardest to analyze, right? Because there are some points that it can be treated as laminar, and there are some points that it can be treated as turbulent, right? And we don't know when we should treat it as laminar, when we should treat it as turbulent, right? So we don't really discuss this in this course, or in any of your courses. And if your Reynolds number is larger than 4000, we are going to assume, your flow is going to be fully turbulent. This is a term, fully turbulent. Or some people call it wholly turbulent. Okay? So, is there any questions here? Do we understand the different types of flow and the transition, all of those things, right? Do we understand this? Okay, let's move. So let's talk about the flow pattern inside the pipe. What is going to happen inside the pipe itself? Let's say we have this pipe. Flow is coming in with V infinity. And we want to see how would the flow look like? What would be the shape of the flow inside this pipe? What is going to happen? What would be the flow profile at the entrance? Let's call this the entrance. Velocity profile is going to be essentially the same as the free stream profile, which is a uniform profile. Right? Okay. But as we go inside, what's going to happen, since we are including the effects of viscosity, we are not neglecting it anymore. So this is not an inviscid flow. This is a viscous flow, right? Since we are including the effects of viscosity, your wall shear stress which we already know is calculated using this formula, right, is going to be important. So what would be the effect of that wall shear stress? What is going to happen is, at this point, the fluid layer that is adjacent to the wall is going to lose all of its momentum, all of its energy to the wall. So it will stop moving. Its velocity is going to be zero. The same thing is going to happen here, right? So what you're going to have, let's say these are these fluid layers, right? The one that is closest to the wall, let's say this is your wall, is going to stop moving. Is going to get stuck, or is going to stick to the wall. Okay? So there is one fluid layer that is stuck to the wall, and there is another fluid layer in the middle. Whatever. Let's say this is their mid plane, mid pipe, that is moving at V infinity. So we have one fluid layer that is trying to stop this fluid layer that is closest to it, right? Because they are changing energy, right? Each fluid layer, they are moving on top of each other. One has stopped moving, the other, and is trying to stop the other one as well. But since the fluid layer above it is trying to pull it with the same velocity, this fluid layer won't stop moving, but it will lose a lot of its momentum and energy. Does this make sense? Okay, so velocity, let's say this is the other fluid layer. We will have some velocity, right? A small, let's try to do this. Some velocity, okay? And this velocity is going to increase and increase and increase until this wall loses its energy, loses its effect, and your velocity profile goes back to the uniform profile we already have. Does this make sense? Do we understand this part? But as you go further inside, what's going to happen is that the effects of this wall effects is going to become more dominant. What does this mean? It means that this uniform part of the flow is going to become smaller and smaller and smaller. So velocity profile at this location is going to be having a smaller uniform flow. This part is the uniform part. This part is the uniform part, at which the velocity is equals to V infinity. And as you go further in, there is one point that your velocity profile will be completely non-uniform. So the wall effects or the viscous effects are going to become completely, fully dominant. Do we understand what is happening here? Right? The fluid layer closer to the wall will lose all of its momentum energy, will get stuck. It will try to stop the other layers as well. But at the beginning, it doesn't have enough energy. So it will just slow down some layers, right? As you go further inside, it will gain more energy, right? It can stop more layers, or it can slow down more layers until your flow becomes non-uniform. And this location, the location at which your flow has become non-uniform, is called the entrance length, before which your velocity profile is changing. This is called the entrance region. And after this flow is called fully developed. So a fully developed flow is a flow that has in which viscous effects are going to become dominant all over the pipe. Okay? What's going to happen? What is the importance of this distinction? Before this, your velocity profile is changing, right? You have some uniform part, you have some non-uniform parts. But after this, your velocity profile is going to remain constant, right? It doesn't matter where you are at your pipe, your velocity profile is going to look like this, okay? It's going to look the same. And these regions, and this is something that you will discuss further in your heat transfer course, but the regions in which you have this velocity gradient, non-uniform velocity that goes from 0 to V infinity, 0 to V infinity. These regions are called boundary layers. I don't know if you see this purple. Do you see this purple chalk? No? Let's see what we have. Let's use a red one. What about this? Is it better? Okay. So these regions are called the boundary layers. So fully developed flow starts where the two boundary layers on top and the bottom wall merge. This essentially means that the viscous effects are going to cover all of the flow, right? When the two boundary layers merge, that's where your fully developed flow starts. Okay. Is this clear? Is this clear what is happening here? Okay, that's good. The first question, after determining the type of flow, the second question you need to answer is that how large is this entrance length? Okay. And we have two equations for it. One is only applicable to the laminar flow, and the other one is only applicable to turbulent flow. We can find the entrance length using this function. Your entrance length, L, let's call it L, E, entrance length, divided by the diameter of the pipe is going to be equal to 0.06 Reynolds number for laminar flow. And it is going to be equal to 4.4 Reynolds to the power 1/6 for turbulent flow. Okay? So we can determine how large this is compared to all of the pipe. If you are dealing with a 1 meter pipe and your entrance length is 1 centimeter, which is 1% of the total pipe's length, it essentially means that you can say this part, the entrance part, doesn't really affect the pressure loss because we have this huge other part that has the fully developed flow. And we can use the simpler calculations, simpler analysis, or simpler equations that we have to calculate the pressure loss, pressure drop inside the pipe. Just neglect the entrance part and do the calculation for the rest of it, fully developed flow part. But if this entrance region is large enough, let's say 10% of your pipe length, then you need to include this part in your analysis. But this analysis of this part is a little complicated. We are not going to focus on it at all. And it's usually easy. It usually doesn't really, it's not that long compared to the pipe length. So we can easily neglect this part. So if in a homework problem or exam problem, you were asked to determine whether the entrance part, entrance region is important, whether we have to include it in the analysis or not, then you need to calculate the entrance length first. And if it was less than 5% of your total length, then you can safely say, no, it is not important. I don't need to include it in my analysis. Let's actually show this, see this on a graph. Let's say we have, on this graph, we have delta P, your pressure drop, as a function of length. So X, pressure drop at different locations. So this is your X, right? At different locations inside the pipe. And let's call this, let's say this is your entrance length. What is going to happen is your pressure drop is going to be nonlinear in the entrance length region. And then after your flow has become fully developed, is going to become linear. See? This, at this point, if your length is L, which is twice the LE, your pressure drop in the entrance region accounts for 50% of the drop. So if you don't include this in your analysis, you're making the wrong calculations. But if your L is, I don't know, let's do LE as here. Let's say LE is here, and then your L is 10 times, 20 times, whatever, this many times bigger. Your pressure drop here is going to be this much, and then you will have a constant linear drop until you get to this point, L, right? So most of this pressure drop is happening in the fully developed region. So if you remove the entrance region, you're not losing that much. You're not sacrificing the accuracy of calculations. Does this make sense? Okay, so let's see how we can calculate the pressure drop and the velocity profile inside the pipe. The first thing we need to, or we are going to employ here, is the force balance. So F, or the second Newton's law, F equals to ma. Let's say you are in a fully developed flow. Again, when you have a fully developed flow, your velocity profile is going to look like this. At every location, right? And let's choose a control volume inside this pipe. Okay. This is part phase A, phase 1, phase 2. Pressure here is going to be P1. Pressure here is going to be P1 minus delta P, right? Minus the pressure drop in this control volume. Since we are dealing with a viscous flow, we need to include the shear as well. Okay. So force balance in this direction is going to be equal to P1 minus P1. That's your force per unit area. So we have to multiply it by the cross-sectional area, right? This is a side view. You have to multiply it by this area, pi r squared, right? Let's say this is r. And what else do we have? We have this area, this force that is in the opposite direction. So a negative sign, P1 minus delta P multiplied by pi r squared. These are sigma of forces, sigma F. And minus, what is the area on which this surface, this shear stress is being applied to? It's the area of the cylinder, right? So that's going to be pi tau. What is the area of the cylinder? It's the perimeter of the circles multiplied by this length. So 2 pi r L. Is it clear? All of the forces that applies to this control volume. And this is equals to 0. Why is this 0? Because there is no change in velocity between these 2 points. That was the main idea of the fully developed flow. Okay. So as you can see, this will cancel out with this and this part of it. So we're going to get delta P multiplied by pi r squared equals to tau 2 pi r L. So we have a function that relates your delta P to the shear. But this only applies to this control volume. To this specific control volume. What should we do to be able to apply it to all of this pipe? The first thing you need to do is to make sure that you are calculating the shear stress at the wall, tau of W. We need to find the relationship between tau of W and tau. And you don't need to do the analysis. I'm just going to give you the relationship. Tau is equals to 2 tau WR divided by the diameter, which this essentially means that your tau changes linearly as you go from this location to the middle. Okay. So let's plug that in here. Delta P pi r squared is equals to 2 tau WR divided by D multiplied by 2 pi RL. This will become R squared. Will cancel with this. The pi's will cancel out as well. And combine these two as 4. So your delta P is going to be equal to 4 tau of wall, length of the pipe divided by diameter. As long as you have the wall shear stress, you should be able to find whatever you are looking for, the delta, the pressure loss. Okay. Is there any questions here? So we have the pressure loss as a function of wall shear stress. But then the question is, how can we calculate the wall shear stress itself? We already know this equation exists, right? dy. And since we are dealing with radius of a pipe, we can do, instead of y, we can replace y with r, right? We already know that this relationship exists. So if we can find the velocity profile, we will get and we will have an idea about the wall shear stress, and we can relate delta P to the wall shear stress and eventually the velocity profile. We are not going to go through the derivations of it, but I'm going to give you the final velocity profile as a function of radius. The final velocity profile is going to be equal to delta P d squared divided by 16 mu L multiplied by 1 minus 2r over diameter squared. And that's it. What is the maximum velocity here? If this is your velocity profile, what is the maximum velocity? How can I have that equation? I want to find the maximum velocity. In general, to find a minimum and maximum, what you want to do is to take the derivative, set the derivative equal to 0, find that r, that right at the maximum and the minimum, the derivative is 0, right? You remember this from mathematics, right? And you find that r, you plug the r here, and find the maximum velocity. But here, we don't really need to do that. Just have to be a little creative. So think about it. This is a value multiplied by 1 minus a value that is always constant or 0, right? So we are always multiplying this by a value that is either 1 or less than 1, right? So we are going to get the maximum velocity when this part of your equation is 1. Does this make sense? Okay. So when do we get that? And when this part of the equation, when does this part of the equation become 1? When your r is 0, right? Essentially at the middle of the pipe. This is going to give you the maximum velocity. So your maximum velocity, your book also uses VC for this, is going to be equal to delta P. This has to become 1, right? D squared divided by 16 mu L. Okay. We can also find the volume flow rate here using this maximum velocity or volumetric flow rate. Q as d to the fourth delta P divided by 128 mu L. And let me just give me 1 second, guys. I think I have the wrong equation on my notes here. Just 1 second, just to double check this. And I'm sorry. Okay. Do you have any questions? Is this all clear? Okay, that's good. Sorry, just want to make sure that we have the correct. Yeah, that's what I guess. There is also a pi here. Pi d4, the volumetric flow rate. So we have the maximum velocity. We have the velocity profile. We can also write the velocity profile using the wall shear stress, right, instead of the pressure loss. And using the wall shear stress, we are going to get tau W divided by 4 mu, right? Okay. 1 minus 2r divided by, this is, we can do r. So we have the velocity profile, and this is all for laminar flow. That's something that you have to keep in mind. And we have the velocity profile, we have the pressure loss, we have the we have an idea about the flow rates. The next step is to analyze a case where your pipe is not horizontal. Okay, what do you think will happen to your pipe? I shouldn't have wiped the force balance here. That's all right. Let's say this is your horizontal plane, and this is your pipe. The first thing you want to do is to find the control volume inside. And what would be the forces that are present here? We have the shear force, the same as before. We have the pressure force here and here, shear force. But what is the extra force that we didn't have in the previous case? That's actually, this type is a very common type of piping, right? A pipe that is not horizontal. What do you think that is? What do you think is the other type of force that we didn't include in our analysis before in the sigma F equals to ma? So in this case, we had P1 pi r squared, right, minus P1 plus delta P pi r squared minus tau 2 pi RL, right? That was the idea. And that is all equals to 0. These were all of the forces in this direction. We want to write the force balance again in this direction. What is one force that we need to include here? Yes. It's the gravitational force. It's essentially your weight. Weight will always be perpendicular to the horizontal plane. That's the idea. So it will have a component in this direction. As long as you know the angle, the tilt angle, you should be able to calculate your gravitational influence, right? So what would be the gravity, that gravitational force is going to be added as that component of gravitational force is going to be W sine of theta, or gamma G sine of theta. Gamma is rho G, right? Gamma, what am I missing? Gamma L. Unbelievable. Gamma L sine of theta, the length of the pipe. Okay? So what this means is that your final equation is going to be equal to your pressure loss equation will have a component delta P minus gamma L sine of theta divided by L is going to be equal to 2 theta divided by R. Okay. Which will be the result of that force balance over there. And eventually your volume flow rate is going to be equal to pi multiplied by delta P minus gamma L sine of theta divided by 32 or 128 mu L. There's also a d squared here. So the only thing that is being added here when you are dealing with a tilted pipe is the influence of gravity. So essentially, the only thing you need to know here, the only extra thing you need to know here is the pipe's tilt and the gamma of your system. Okay. There is one section of this chapter that we don't really, we are not going to talk about at this point because we need the knowledge of chapter 6 to talk about this. And so I'm going to skip that part for now, but we will come back to it when we are talking about chapter 6. Okay. So we have the pressure loss using the force balance. Next step is the dimensional analysis. Let's see what we can get from a dimensional analysis. Right? The main thing we discussed in dimensional analysis was the two main dimensionless parameters that are very important in pressure drop inside the pipe, right? If you recall, we are talking about pressure drop inside the pipe, and we came up with all of the dependence of the pressure drop inside the pipe, right? Eventually, we said that we have two dimensionless parameters that is going to define the relationship between the pressure drop inside the pipe and its Reynolds number. Right? This is the Reynolds number. And this was another dimensionless parameter that we haven't named yet. Okay? So I just have to double check every equation that I write here, because I can't, I'm just writing them off of memory. Okay, so let me just make sure that we are having the correct. Okay, so this, yeah, d divided by L. Yeah, see? That's what I say. I'm sorry, guys. This printout has come out as garbage. I'm just writing these equations as out of memory. So we have d divided by L, delta P divided by rho V squared divided by 2. This part of the equation we already know is that the right-hand side of the equation we already know is the Reynolds number. But the left-hand side, we haven't named it, but we have seen this in the previous lecture. We are going to call this the friction factor, F. So pressure drop in the pipe is directly related to the friction factor. That's d divided by L, delta P, rho V squared divided by 2. And on the other side, it is related to the Reynolds number. For a laminar flow, we can actually find that your F, friction factor, is equals to 64 divided by Reynolds number. As long as you are within the laminar flow region. Okay? What does this mean? If you have to plot how friction factor changes with Reynolds number in the laminar flow, this is what it is going to look like. Okay, just a linear pattern. As you increase the Reynolds number, your friction factor is going to decrease. And that will be the result of the dimension analysis. If you go through the chapter, you will see that they have done the whole Buckingham Pi theorem again, but we have already done that part. We have already found out the constants, the dimensionless parameters. You don't need to go over it again. As long as you understand that this is the relationship between the friction factor and the Reynolds number in the laminar flow, you should be fine for these parts. Okay. I'm sorry about the problem with my notes. I just have to go over the book. We can actually find the friction factor as a function of wall shear stress as well. Just F is equals to 8 wall shear stress divided by rho V squared. Okay. And that will be it for the laminar flow part of the discussion. Just make sure I'm not missing anything. Okay. Yeah. Is there any questions from the laminar part of the discussion, laminar flow part of the discussion? It is not that hard to understand. We don't have that many hard equations, tough equations we need to deal with. As long as you understand the concept, it should be fine. But again, as you increase the Reynolds number, you are going to increase the chances of seeing a fully developed turbulent flow. The same ideas apply here. If I were to tell you to find the pressure loss inside the pipe for a turbulent flow, the first thing you need to do is to calculate the entrance length, right? And compare it to the pipe length. If it was small enough, let's say less than 5% of the pipe length, you should be able to assume that all of the pipe is fully developed, right? But dealing with turbulent flow is much harder than dealing with laminar flow. Why is that the case? Because let's say, again, let's say this is your pipe, and this is your fluid particle that is moving. Okay. If you were to plot your velocity of this fluid particle with respect to x for a laminar flow, this is what it will look like. So laminar flow. But if you were to plot it for a turbulent flow, what you're going to see is this type of fluctuation. That's the velocity at this point, right? Either with respect to time or with respect to location, doesn't really matter. You should see the same pattern. This essentially means that your velocity will fluctuate. And this is something we need to find, the velocity profile. This is something we need to have to be able to find the friction factor, to find the pressure loss, to find all of the like wall shear, all of those other parameters. We are actually getting close to the end of the class. So I don't know if I should start this discussion. Let's just say this, and then we'll leave the rest of it for the next class. So what are we going to do with this velocity pattern? We are going to divide the velocity at each point to the fluctuations u prime plus an average velocity, u bar. So we are going to find the average of this velocity profile, right? Let's say this is the average line. And then we are going to separate the fluctuations. If you do so, you can treat this time average velocity profile as a laminar flow, and then you just have to find a way to deal with the fluctuations, right? Does this make sense? We are going to continue this discussion in the next lecture, and we will finish. I'm not sure, though, because we are a little behind. We went a little slower than I expected. But hopefully, we will finish chapter 8 on Thursday. And on Tuesday, we will do an exam review. Your homework is uploaded. I uploaded the homework on Saturday. You have till Tuesday to submit your homework, right? Before the exam review. So if you had any problems for the homework, we can talk about it during the exam review. Your homework is only, I think it's only chapters 4 and 5, yes. It will be on the final exam, not on the second exam, no. Chapter 8 will be, so, okay, that's a very good point. That I think I forgot to mention it. So just to make things a little easier for all of us, it's going to be easier for me as well. Your exam 2 will be chapters 4, 5, and 7. Your final exam will be chapters 1, 2, 3, 8, 6, and 8. Okay, so only 5 chapters for the final exam, 3 chapters for the exam 2. Since we are hopefully getting rid of exam 1 altogether, right? These 2 exams will be your main source of the grade, right? Plus homework, plus the bonus points, plus whatever. Right? Does this make sense? Okay. Is this something that you would prefer, or you want to have a comprehensive final exam? You don't want to have a comprehensive. Okay. That's what I guessed. Okay, so that's it. Have a good day. See you on Thursday. And don't forget about your homework. There is a possibility that I need to cancel the class on Thursday because I'm taking my second shot of the vaccine today, and usually people fall ill. So if I do fall ill, we will cancel the class. If not, I'll see you on Thursday.